Dear students, today we shall learn about this module which talks about the chemical shift and its measurement. Learning outcomes. After studying this module, you shall be able to understand the position, intensity and shape of an absorption band, understand the shielding and deshielding effects, understand the measurement of chemical shift value, understand the meaning of equivalent and non-equivalent protons, understand the meaning of homotopic, enantiotopic and distereotopic protons. Introduction. Now students learn about the introduction of this chemical shift and what does it mean. In general, there are 4 different features of a NMR spectrum which provide important information about the structure of a particular compound. First is the number of signals involved. The number of signals gives the information about how many different types of hydrogens are actually present in a molecule that is being determined. Position of the signals, that is also called chemical shift. The value of chemical shift is determined by the nearby environment of each hydrogen, and thus we get information about the local electronic surroundings of each hydrogen which is present in the molecule, whose structure is to be elucidated. Now, intensity of signals. The intensities of signals tell us the number of identical hydrogens present in the particular molecule. Spin-spin splitting of signals. The splitting of each signal tells about the other groups present in the proximity to that of a particular hydrogen. An NMR spectrum is a plot of the intensity of a peak against chemical shift measured in parts per million, that is ppm. Chemical shifts are reported on the horizontal axis, that is the x-axis of the spectrum. Most protons absorb between 0 to 12 ppm. The terms upfield and downfield describe the relative location of peaks. Upfield means the low value of chemical shift, that is towards the right hand side, and downfield means the high value of chemical shift, that is towards the left hand side. In a molecule, each type of proton has a different electronic environment and shows the signal at different value of chemical shift. All these values are measured relative to the position of a reference peak at 0 ppm on the delta scale due to tetramethylsilane, that is TMS. TMS is a volatile inert compound that gives a single peak at 0 ppm value. Now students, let us take a deeper insight into shielding and deshielding effects. When a molecule is placed in an external magnetic field, the electrons surrounding a nucleus start to circulate perpendicular to the applied magnetic field, and they produce a secondary magnetic field or a local magnetic field called as induced magnetic field, which opposes the applied magnetic field in the region of the nucleus. Thus, the nucleus experiences a weaker magnetic field than the applied magnetic field and is said to be shielded. The difference between the applied magnetic field and the induced magnetic field is known as nuclear shielding. The magnitude of the induced magnetic field is directly proportional to the magnitude of the applied magnetic field. The higher the electron density around a proton, the higher is the diamagnetic shielding. Circulation of electrons about nearby nuclei generates an induced magnetic field that can either oppose or reinforce the applied magnetic field at a proton. depending upon its location in the induced magnetic field. If the induced magnetic field generated by an electron around the proton opposes the applied magnetic field, the nucleus in turn experiences a weaker magnetic field than the applied magnetic field, and the proton is said to be shielded. This type of shielding is called as diamagnetic shielding. On the other hand, if the induced magnetic field reinforces the applied magnetic field, the proton experiences a higher field strength. Such type of proton is said to be de-shielded. This type of shielding is called as paramagnetic shielding. This can be easily seen in the figure where you can see the de-shielded and the shielded proton. And you can also see the downfield and the upfield values of de-shielded and shielded nuclei. Now students, compared to a naked proton, a shielded proton requires higher applied field strength, whereas a de-shielded proton requires lower field strength for this transition. Thus, shielding shifts the absorption upfield and de-shielding shifts the absorption downfield. Such shifting in the NMR absorption positions is known as chemical shift, and it arises from the circulation of electrons in particular type of chemical bonds. Now, the induced magnetic field is not uniform over the entire molecule, and hence each nucleus experiences a slight different local magnetic field strength. Therefore, their absorption signals appear at different values. The signals in proton NMR spectra give information about different kinds of protons and their chemical environment in a particular molecule. Let us now come to chemical shift values. Each proton in a molecule is in a slightly different chemical environment, and hence they do not have much difference in their resonance frequency. This difference is very little in comparison to the instrument field strength, that is 60 MHz. Therefore, it is very difficult to measure the exact frequency values of each proton accurately. However, the relative frequencies can be determined with more accuracy. For this reason, a reference compound is added to the sample and resonance frequency of each proton is measured relative to the resonance frequency of the reference compound that is involved. Tetramethylsilane, that is TMS, or the chemical formula is CH3 whole 4 silicon, is most commonly used as a compound as a reference. The frequency of various signals can be measured in terms of hertz by putting TMS at 0 Hz. This compound is chosen particularly because of the properties. First, it is chemically inert and miscible with a wide range of solvents. Secondly, it gives a single sharp peak as it has 12 chemically and magnetically equivalent protons. Third reason, it is highly volatile and hence can be easily removed if the sample has to be removed. The protons of this methyl group are more shielded than the protons of most organic compounds due to low electronegativity of the silicon atom. Hence, the NMR of a particular proton in a molecule will appear at different field strength compared to the NMR signal from TMS. The resonance position of the protons of TMS is assigned 0 on the delta scale, and the other protons are measured with respect to this particular position. Now let us now come and shift our focus to measurement of the chemical shift. Chemical shift when measured in hertz is directly proportional to the strength of the applied magnetic field. Therefore, these values will vary with the strength of applied magnetic field. Hence, if a chemical shift is given in Hertz, the applied frequency should be mentioned. The NMR instruments of different field strengths are available, and hence it is advisable that the chemical shift should be expressed in terms of which are independent of field strength. One such unit is delta. The chemical shifts are generally expressed in delta values whose units are ppm, that is parts per million, and it is independent of the field strength. The chemical shift of a particular proton is defined as the difference in Hertz between the resonance frequency of the proton under observation and that of TMS divided by the operating frequency of the spectrometer. Putting this mathematically, delta is equal to observed frequency from TMS in Hertz into 10 to the power 6 whole divided by operating frequency of the instrument in Hertz. Now let us take an example of the same. When benzene is analyzed using an NMR spectrometer operating at 300 MHz, the protons of benzene absorb at a frequency that is 2181 Hz larger than frequency of absorption of TMS. The chemical shift of these protons is calculated using the same formula as stated by me above. Delta is equal to 2181 Hz into 10 raised to power 6 divided by 300 into 10 raised to power 6 Hz. This gives a value which is unitless, is equal to 7.27 ppm. Now, if a 60 MHz spectrometer is used instead of a 300 MHz instrument, the protons of benzene absorb at a frequency of RF radiation, that is 436 Hz, larger than that of frequency of absorption of TMS. The chemical shift of these protons is calculated instead of 300 in the same formula we put 60, and instead of 2181 Hz we put the value of 436 Hz. Now similarly we get the value of 7.27 again. Thus the chemical shift value does not depend on the operating frequency and it is a dimensionless value. That is why chemical shifts have been defined in relative terms on the delta scale rather than in absolute terms, that is Hertz. If signals were reported in Hertz, the precise frequency of radiation absorbed, then the frequency of absorption would be dependent on the strength of the magnetic field and would not be a constant value. For most organic compounds, the signal produced will fall between the range of 0 to 12 ppm. In rare of the rare cases, it is possible to observe a signal occurring at a chemical shift below 0 ppm, which results from a proton that absorbs at lower frequency than the TMS, which is our reference compound. Most protons in organic compounds absorb at higher frequency than TMS. So most chemical shifts that we encounter will be positive numbers. Chemical shift can also be measured on a tau scale, in which TMS is given a value of 10 ppm. The value in delta can be converted into tau. This mathematical equation is used to describe tau is equal to 10 minus delta. So values in delta can be easily converted into their tau values using this relationship. Now students, let us learn about the number of signals, that is chemical equivalence and non-chemical equivalence, and how many signals do they give rise to. The number of signals in a proton NMR spectrum indicates how many different kinds of protons are present in a molecule. This is due to the fact that the protons in different electronic environments absorb at different field strength and hence different chemical shifts. Protons that have same chemical environment are known as chemically equivalent protons and they have the same chemical shift. In methyl acetate, for example, there are two types of protons. The 3 protons labeled as HA having a different chemical shift value than the 3 HB protons, because the two sets of protons are in different chemical environments, that is, they are chemically non-equivalent. On the other hand, students, the 3 HA protons are all in the same electronic environment and are chemically equivalent to one another. They have identical resonance frequencies and the same can be said for the 3 HB protons. Now, how do we test for the equivalence of protons? Let us look into this aspect. The concept of equivalence can be approached in two ways. First method, look for the symmetry element, that is axis of symmetry and plane of symmetry in a particular molecule that is under consideration. Two protons are chemically equivalent if they can be interchanged via a symmetry operation, either rotation or reflection. The following examples will clearly illustrate the relationship between symmetry and chemical equivalence. Now let us begin by considering the two protons on the middle of carbon of propane. Imagine that this molecule is rotated 180 degrees about the following axis with your eyes closed. When you open your eyes, you cannot determine whether the molecule was rotated or whether it was not rotated. From your point of view, the molecule appears exactly as it was before you rotated it, and it therefore has an axis of symmetry. The two protons in the middle of the carbon of propane are interchangeable by rotational symmetry and hence they can be called as chemically equivalent protons. Now come to the second method. Another method is the replacement method. For the protons which are to be tested whether they are chemically equivalent or not, we can replace each proton in turn by another atom or group not present in that molecule. Compare the two structures formed. If they are identical, then the protons are homotopic. If they are enantiomers, the protons are enantiotopic. And if they are distereomers, then the protons are distereotopic. If they are structural isomers, the proton are heterotopic. The homotopic and enantiotopic protons have the same chemical shifts, whereas distereotopic and heterotopic protons have different chemical shifts. Let us now consider each of these types of protons separately. First, homotopic protons. Some examples of homotopic protons. The homotopic nuclei are interchangeable by rotational axis of symmetry, as explained to you in the example of propane just earlier. In each of the following examples, the two protons shown in red color, as you can see in the figure, are homotopic because as you draw the two structures by replacing each one of these protons with deuterium, both these structures represent the same compound. That means these protons are homotopic in nature. This can be easily seen in the figure that you can see. You obtain the same compound after replacement with deuterium. Let us now come to the second type of protons, that is enantiotopic protons. When a carbon is bonded to two hydrogens and to two different type of groups, the two hydrogens are known as enantiotopic hydrogens. The enantiotopic nuclei are interchangeable by reflection or a plane of symmetry. Here are some examples of enantiotopic protons. In each of these examples, the two highlighted protons are enantiotopic, as you can see in the figure. As you draw these two compounds each time replacing one of the protons with deuterium. Then determine the relationship between the two drawings. If they are enantiomers, then the protons are enantiotopic. You can do this easily by looking at the figure and doing it on your own. Distereotopic protons. If the two protons are neither homotopic nor enantiotopic, then they are not chemically equivalent. Consider the protons on C3 of R2 butanol. We say R from the Khan in gold Prelog notification, as you have learnt. These protons cannot be interchanged by either rotational symmetry or reflection or plane of symmetry. Therefore, these two protons are not chemically equivalent. If you replace these two hydrogens with another atom or group, say deuterium, each at one time, and if it produces a pair of distereomers, then these protons are known as distereotopic protons, which have different chemical shifts and show two signals in the NMR spectrum. Distereotopic protons cannot be interchanged by symmetry, and this is the most important differentiating point between homotopic, enantiotopic and distereotopic protons, students. This can be clearly seen and done by seeing this figure. Now we should note the following point. While determining the relationship between two protons, first determine if there is an axis of symmetry that interchanges the protons. If there is, then the protons are homotopic, whether or not there is a plane of symmetry. If the protons cannot be interchanged by rotation, then look for reflectional symmetry. If there is a plane of symmetry, then the protons are enantiotopic. Now, by following this particular table and flow chart, you can see whether the protons are enantiotopic, homotopic and distereotopic, and decide for your own whether it has a reflection symmetry or rotational axis of symmetry, and you can decide which proton is homotopic, enantiotopic and distereotopic. If two or more protons are in a same equivalent environment, then they will have the same chemical shift and appear as one signal. In a methyl group, CH3 group that is, all three protons are always equivalent. In a methylene group, the true protons are also equivalent unless adjacent to a chiral center. In the chair conformation of cyclohexane, axial and equatorial protons occupy a different electronic environment and hence they are not chemically equivalent. They cannot be interchanged by a symmetry operation. Consequently, we might expect two signals in the proton NMR spectrum, one for the 6 axial protons and the other for the 6 equatorial protons. But the proton NMR spectrum of cyclohexane exhibits only one signal. Now, why is that? The observation can be explained by considering the rapid rate at which ring flipping occurs at room temperature. The NMR spectrometer is too slow to acquire a spectrum of a single chair conformation. While the spectrometer is acquiring the spectrum, the ring flipping is rapid between the two chair conformations, producing a blurry picture. The spectrometer only sees the average electronic environment of the protons, and hence only one signal is observed. However, students, if the sample of cyclohexane is cooled inside the spectrometer, the ring flipping process occurs at a very slow rate. If the sample is cooled to 100 degrees Celsius below zero, that is minus 100 degrees Celsius, ring flipping occurs at a very slow rate, and separate signals are in fact observed for the axial and the equatorial protons. Now you can see the axial and equatorial protons in the figure given, and at very low temperatures separate signals are observed for both of these two. Now let us study a bit about the signal area. The area under a peak in proton NMR spectrum is proportional to the number of protons in a given chemical environment in a molecule. For example, if the area under a peak is 2 times the area under another peak, then there are twice as many protons responsible for the larger peak than for the smaller one. In this way, by integrating the different NMR peaks, information regarding the relative number of chemically distinct hydrogens can be found. The integration values do not always correspond to the exact or absolute number of protons. Instead, it tells us the relative number of different hydrogens or the ratio of the amount of equivalent protons. This is an important relationship when samples incorporating 2 or more sets of hydrogens are examined, since this relationship allows the ratio of hydrogen atoms in each distinct set to be determined. Now students, in the proton NMR of ethanol, which is shown with the integral line which is shown also, there are 3 distinct types of protons in ethanol. Due to 3 hydrogens in the CH3 group, 2 hydrogens in the methylene group and 1 hydrogen in the OH group. And the integral line is shown in orange. Therefore, 3 peaks will be observed in the spectrum in the relative area of 3:2:1. Note students, when evaluating relative strengths of signals, it is helpful to set the smallest integration to unity and convert the other values proportionally. Integrals are not normally displayed in 13C NMR spectra, and the peak heights are not a reliable indicator of the number of carbons in each environment. This is the major important point of difference between proton and 13C spectrum. Now an important point here students is that it is necessary to measure the relative strength as well as the chemical shift of resonance signals that comprise an NMR spectrum in both cases of proton and 13C NMR in order to correctly elucidate a particular compound. Now let us summarize this module students. The proton NMR has 3 characteristics of every signal. The first characteristic is the position of the signal, called its chemical shift delta. Second is the number of signals, that is number of non-equivalent hydrogens. Third is the integration, which is described by the relative number of hydrogens present at each signal. The last one is the splitting, which represents the number of neighboring hydrogens. Secondly, the left side of an NMR spectrum is described as downfield and the right side is called as upfield. The area under the peak in proton spectrum is proportional to the number of protons in a given chemical environment in a molecule, and it also gives information regarding the relative number of chemically distinct hydrogens. The 2 or more than 2 protons which are equivalent by symmetry, either by axis of symmetry or plane of symmetry, are said to be chemically equivalent. The homotopic and enantiotopic protons have same chemical shift, whereas distereotopic and heterotopic protons differ in their chemical shifts. The homotopic protons can be divided by the axis of symmetry or reflectional axis, whereas enantiotopic proton by a plane of symmetry, but distereotopic protons are not related with any type of symmetry element. I hope you have learnt about chemical shift and the signals obtained from chemically equivalent and non-equivalent hydrogens nicely in this module. Thank you, students.